Hi, in this presentation, we are going to discuss some important properties of prime numbers. Specifically, we are going to delve into two very important properties of prime numbers, one of which is known as the Euclid's theorem, a very famous result which talks about the number of primes. And the second property gives us uh, an upper bound for the nth prime number as such. Okay, so first we look at the statement of Euclid's theorem. The statement is very straightforward to look at. It says that there is an infinite number of primes. That is to say that if you start counting the primes, there is absolutely no limit to the number of primes, so that the number of primes is infinite. Or in other words, you can also say that there is no such thing called the largest prime number, right? It's equivalent to saying that there is an infinite number of primes. Okay, we're going to prove this using the method of contradiction as follows. A very straightforward result. Okay, so to begin with, uh, as I said, we are going to prove by the method of contradiction. So, what do you mean by the method of contradiction? In this method, what we do is we'll take the negation of what we are supposed to prove, and we will show that there is a contradiction at the end because of the reason that we have taken the negation of the statement to be proved. So automatically we see that statement holds good. So that means to say that for us to show that there is an infinite number of primes, we assume that we suppose that the number of primes is finite. Okay, that is, if we try to list the primes in an order, say P1, P2, and so on. That means P1 is going to be the first prime, which is 2, obviously. Same way, say if we take P2 to be the second prime, which is 3, and so on, we suppose that Pn is the last prime. Okay, so that means say that the list P1, P2, P3, etc. Pn, this contains all possible primes, obviously, and Pn is supposed to be the last prime, say, if possible. Then what we do is we'll consider the integer capital P, which is defined as P1 into P2 into P3 and so on into Pn plus 1, right? So as you can see, if you take P to be the integer defined as this, which is basically the product of all the primes plus 1, then obviously since Pn is the last prime and this P, capital P is bigger than Pn, we see that P is composite, right? So P has to be composite because it is greater than Pn. P is greater than Pn, correct? So now since P is composite, obviously there exists a prime, say P, such that P divides capital P. That's exactly what we mean by composite number. Of course, P is a number greater than 1, obviously, because it's a number greater than 1, it's an integer greater than 1, and because it is composite, it should so happen that there must be a prime, say P, such that P divides P. Right? Now look at this. This implies that P divides. Now, obviously, because P divides P, capital P is nothing but P1, P2, P3, and so on, Pn. Right? So P has to divide P1, P2, P3, etc. product Pn, and the same P should also divide P1, P2, P3, and so on, Pn plus 1. Now, why is this? This is because P1, P2, P3, etc. Pn plus 1 is nothing but capital P. So P divides P, so automatically this happens. And why does this happen? This is because P is a prime, and because it's a prime, it has to be one of these PIs. Because we have taken P1, P2, P3, etc. to be the list of all the primes, so that P has to be one of these primes. And because P is one of these primes, it must divide the whole product P1, P2, etc. Pn. Right? So now we have got that P divides P1, P2, etc. Pn, and P also divides P1, P2, etc. Pn plus 1, which automatically implies that P divides this minus this, or this expression minus this, because as we know, if A divides B and A divides C, then A divides all linear combinations of the form Bx plus Cy. Correct? So automatically P divides the difference of the two numbers. And what do you get as difference of the two numbers? Obviously, this after cancellation gives us 1, because this product P1, P2, etc. Pn is the same as this product P1, P2, etc. Pn. So the 2 will get cancelled off and we'll be left with 1. But is this possible? Of course not. This is a contradiction because P is a prime, right? Since P is a prime, any prime cannot divide 1, right? So this is a contradiction. And why did we get this contradiction? It is because we supposed that the number of primes is finite, so that supposition itself is false. Hence, the number of primes is infinite. So that completes proving the Euclid's theorem. Of course, before ending proving this theorem, let me tell you this. The name of this theorem is Euclid's theorem, and you should not get confused with the name of this with that of Euclid's lemma. Euclid's lemma is different, and Euclid's theorem is this one, and obviously this is different. So from the examination point of view, you might be told to state and prove Euclid's theorem, or you might be simply told to prove that there is an infinite number of primes, or you could also be told to prove that there is no largest prime number. Whatever the statement is, the proof is going to be exactly the same as such. Right? So this completes the proof of this theorem. Now moving on to the next result that I want to discuss. The next result is this. As I told you initially, this result talks about an upper bound for any prime number. What do you mean by an upper bound? It means that any prime number can only be less than or equal to a particular bound, which is called an upper bound here. Okay, so this is exactly what we are supposed to prove, and the proof for this is by the method of contradiction. So we prove the result by contradiction. Now, what is the method of contradiction? I would also say method by, sorry, it is not by the method of contradiction, I'm sorry, by the method of induction. I'm very sorry. Yeah, so we're going to prove this result by the method of induction. Now, before proving this result, let me tell you what the statement means. What does it mean? If Pn is the nth prime, then this Pn is always less than or equal to 2 to the power 2n minus 1. For example, if I call P1 or Pn as the nth prime, obviously P1 is supposed to be the first prime, and that's going to be 2. P2 is going to be 3. P3 is going to be 5. P4 is going to be 7, and so on. Right? Now, according to this theorem, what is going to happen? Pn, that means P1, if I take 2, is always going to be less than or equal to 2 to the power 1 minus 1. Is that so? What is 1 minus 1? It is 0. 2 to the power 0 is 1. So 2 is less than or equal to 2. This is going to be true. Now if I take P2, then this number has to be less than or equal to, according to the statement, 2 to the power 3 minus 1. I'm sorry, not 3 miness 1, 2 minus 1, because n is 2 here. Will it work? 2 minus 1 is 1, 2 to the power 1 is 2, and 2 to the power 2 is 4. So obviously 3 is less than or equal to 4. And if I take 3, P3 is going to be 5, in which case we are supposed to have that 5 is less than or equal to 2 to the power 3 minus 1. Is that so? 3 minus 1 is 2, right? 2 to the power 2 is 4, 2 to the power 4 is 16, so obviously 5 is less than or equal to 16, and so on and so forth. Right? This is exactly what the theorem is stating, and of course this, whatever I have discussed just now, is not going to be the proof for this, because we are supposed to prove the result generally, and that is why we use the method of induction to prove this theorem. Okay, so how do we prove any result by the method of induction? So first of all, we verify the result for some basic values of n. So for n equals 1 and n equals 2, we have, what do we get? As I showed here, if we take n equals 1, I get p1 equals 2, and that is obviously less than or equal to 2 to the power 1 minus 1. And if I take n equals 2, p2 equals 3, and 3 is less than or equal to 2 to the power 2. 2 to the power 2 minus 1. So I'll exactly say that itself. What do we get? P1 is going to be 2, and of course 2 is less than or equal to 2 to the power 1 minus 1, and P2 is going to be 3, and 3 is less than or equal to 2 to the power 2 minus 1. Right? So what does that mean? That means to say that the result is verified for n equals 1 and n equals 2. So that means that the result is true for some initial values of n. Okay. Next, we assume that the result holds for all values, of course, all values of n. Here, n is obviously a positive integer that need not be said as such. So we'll assume that the result holds for all possible values of n less than or equal to a particular k as such. Okay. Now, what do you mean by that? That is, what do you mean by this? First of all, this result is true for n equals 1, n equals 2, and so on up to n equals k is what we are assuming. Okay. So we have p1 less than or equal to 2 to the power 1 minus 1. We have actually proved it also. Okay. Then we are going to take p2 less than or equal to 2 to the power 2 minus 1. Okay. And so on. We assume that pk is going to be less than or equal to 2 to the power k minus 1. Okay, so this is what we are going to assume now, and we now prove the result for n equals k plus 1. That is, what are we supposed to prove then? For n equals k plus 1, we are supposed to show that pk plus 1 is going to be less than or equal to 2 to the power what will happen here? If we take n as k plus 1, this will be k plus 1 minus 1, which will eventually give us 2 to the power k. That is, we're going to prove that pk plus 1 is less than or equal to 2 to the power k. So this is what we are supposed to prove. Just shade it just to make you understand that this is supposed to be proved. So for us to prove that this happens, what we'll do is we'll simply consider the left hand side of this expression. Okay. Now, according to an expression that we got in the previous theorem, we can see that pk plus 1 is going to be p1 is going to be less than or equal to p suffix 1, that is basically p1 1 minute. Yeah, P1, P2, etc. Pk plus 1. Okay, so this automatically happens because of the previous theorem. Now, this implies that now what is P1, what is P2, and so on, as we have seen here. Just 1 minute. So, because P1 is less than or equal to 2 to the power 2 to the power 2 minus 1, this is just going to be 2 as such, correct? As you can see here, simplifying this will give this as 2. And what is going to be P2? It's going to be 2 square, correct? So, this will be 2 to the power 2 as such. What is P3 then? It's going to be 2 to the power 2 square, correct? And so on. Or what is going to be Pk? Pk is going to be 2 to the power 2 to the power k minus 1, right? So because each of these is less than or equal to the corresponding power of 2, this pk plus 1 is going to be less than or equal to 2 into 2 square into 2 to the power 2 square into etc. 2 to the power 2 to the power k minus 1 plus 1. Fine. What will this be on simplification? This is going to be, as you can see here in this expression, each of the numbers here has a base as 2. So I can simply add the powers and I can write it as 2 to the power. And what do I get? It as, that would be 2 to the power 1 plus 2 plus 2 square. Am I right? 2 square and so on, plus the last number would be 2 to the power k minus 1. Correct? And you have a plus 1 outside this as such. Right? Now, what would this be? So, I'll now consider only this sum of numbers in the power, which is basically 1 plus 2 plus 2 square and so on, plus 2 to the power k minus 1. As we all very well know, this is a geometric series as such with k number of terms. And as we know, the sum to k terms of the geometric series is given by, yes, if you have a general geometric series with the first term as a and the common ratio as r, then the sum to k terms is going to be a into r to the power k minus 1 divided by r minus 1. Accordingly, here this would be, because the first term is 1, a is going to be replaced by 1 and we will be left with, now what is r? R is a common ratio which is simply 2. So this will be 2 to the power k minus 1 whole divided by 2 minus 1, which is effectively just 2 to the power k minus 1. Correct? So accordingly, what happened? Yeah. Accordingly, what we have here is that, yeah, what do you get here? This would be 2 to the power, yeah, simply 2 to the power 1 second. Yeah, so this will be 2 to the power, this whole power, which is 1 plus 2 plus 2 square plus so on plus 2 to the power k minus 1 is going to be simply 2 to the power k and then minus 1. Mind you, this minus 1 is not in the power for 2. For this 2, it is 2 to the power 2 to the power k minus 1 as such. And we have a plus 1 outside this, so this will be 2 to the power 2 to the power k minus 1 and then plus 1. Correct? Got this right? Okay. Now, I can also see that this 1 can be easily rewritten as 1 less than or equal to 2 to the power 1 second. Yeah, so I can write 1 as less than or equal to 2 to the power k minus 1 for all k as such. Is that so? Check it out. If you can check, take any value of k here, you see that 1 is always going to be less than or equal to this number. Particularly if you take k is equal to 1 or k equal to 0, of course k equal to 0 does not really work as such, but if you take k equals 1, what do you get? You get 2 to the power 1, which is 2, minus 1, which is 1, and 2 to the power 1 is 2. So 1 is definitely less than or equal to 2, and after that it is going to be valid for any value of k accordingly, right? So 1 is always going to be less than or equal to 2 to the power 2 to the power k minus 1, so that if I use this expression here, I see that pk plus 1 is less than or equal to, initially, what is it? Less than or equal to? It is less than or equal to 2 to the power k minus 1 plus 1. And now, this is further less than or equal to 2 to the power k minus 1. And because this 1 is again less than or equal to 2 to the power k minus 1, I would say plus 2 to the power k minus 1. What is this upon simplification? This is going to be, because both are exactly the same, this is going to be 2 into 2 to the power k minus 1. And what will this be upon simplification again? So this will give us simply 2 to the power k. And what have we achieved accordingly in that case? This implies that, yes, what have we got? Pk plus 1 is less than or equal to 2 to the power k. Right? Is that what we wanted? As you can see, this is exactly what we wanted. So we got this to be happening. So now I can say that therefore the result is proved for n equals k plus 1, and because it is proved for n equals k plus 1, and therefore and thus is true for all positive integral values of n, and that completes proving the result as such, right? So effectively, what have we proved? Finally, we have proved that any prime will have its value less than or equal to 2 to the power n minus 1. Remember, this might look like a very simple result or an irrelevant result as such, but it has its own importance because it tells us as to how or where the next prime number would be. If you know that a particular number is a prime, you can find the next prime using this number as such. So this is an upper bound, which will effectively tell us that the next prime cannot be bigger than this number as such. Okay, so this proves this theorem, and with this I'm going to conclude with this presentation. Watch the complete video and make notes. Whatever we have discussed here is going to be important from the subject point of view as well as from the examination point of view. Right, with this I'm going to end this presentation. Thank you for your time.